In this video, we are going to discuss line integrals in complex plane. Complex line definite integrals are called line integrals. That is, in the real domain, you have definite integrals. As an example, let us take integral a to b f of x dx, some function f of x. So what this means is we are integrating this function from a to b over the real line. Okay, so we have the real line like this. This is, say, the point 0, and suppose we are having 2 points a and b. The input points are taken from this interval a to b. Okay, that is, x values are taken from a to b, and we are integrating the function from a to b f of x dx. Now when it comes to complex plane, the scenario is a little bit different. In complex plane, your domain is a two-dimensional plane, that is the complex plane, like this, with the real axis taken as the x-axis and the imaginary axis taken as the y-axis. And the range is also a two-dimensional plane, the complex plane, with the real axis as the x-axis, we call it the u-axis, and the imaginary axis, we call it the v-axis. Now here, when we are integrating a complex function in a complex domain, then we are integrating it over some curve C. Okay, some curve like this. Now the input points are taken over this curve C. In the real domain, it was the input points was taken from an interval AB. Here we are taking the input points from a curve C. So we are integrating a function over this curve C. That is why it is called a line integral. Okay, it is called a line integral. The input points are taken from a curve C. And the first thing that I want to say is, when I mean a curve, it can be a straight line. A straight line or any path is in general called a curve. The notation is integral over C f of z dz. This is what we call the line integral. That is, we are integrating a complex function f over a curve C. Now this curve C should be a smooth curve. That is important. By smooth, we mean C has a continuous and non-zero derivative at each point. Okay, so geometrically this means that it has a continuously turning tangent everywhere. It should be smooth in that sense. It should have a continuous and non-zero derivative at each point. Now this is what we mean by the complex line integral. You must remember, a complex line integral is the definite integral counterpart in the complex domain. Now we will discuss some of the basic properties of the complex line integral. You see, integral of kf, that is a constant times a function f, is k times the integral f of z dz. Okay, we can take the constant outside. Similarly, integral over c k1 f1 plus k2 f2 is equal to k1 times integral f1 plus k2 times integral f2. This is the first property. Second is sense reversal. That is, we have already studied this in your real case. That is, integral from a to b f of x dx is equal to minus integral b to a f of x dx. That is, that whole property holds good in the case of complex functions also. That is, integral z naught to z f of z dz is equal to integral z to z naught f of z dz. The third property is partitioning. So suppose I am having a curve like this, integral over c f of z dz. I am taking integral over some curve c. Now, even if I partition this curve into two different parts, that is integral over C1. I'm from Z0 to this point, I'm going to call it integral over C1, and Z1 to Z, I'm going to call the curve as C2. So even if I split this into two parts, integral of C f of z dz is equal to integral of C1 f of z dz plus integral over C2 f of z dz. Now we are going to discuss the first evaluation method. This is the simplest method. For this, the function has to be analytic throughout the domain. Okay, to use the first evaluation method, the most important thing is the function has to be analytic in the given domain. Only then you can analytic in the given domain D. Only then you can use this method. Now this method is similar to the definite integral in the case of real functions. Okay, so suppose you in real domain integral from a to b f of x dx is equal to f of b minus f of a, where capital F stands for the antiderivative or the integral of f. Okay, similarly when it comes to complex domain also, integral over z0 to z f of z dz is equal to capital F of z1 minus capital F of z2, that is where f is the antiderivative of small f, or capital F is the integral of small f in that sense. As an example, for example, in integral say a to b cos x dx in the case of real functions is equal to sine b minus sine a, because it is sine x from a to b, and that is because sine is the antiderivative of cos. Similarly, integral say z0 to z1 cos z dz, if I'm taking, if this is the complex function cos, that is equal to cos z1 minus cos z0. This we are able to use this because cos is analytic in the domain containing z0 and z1. Okay, we are having some domain D, cos is everywhere analytic, uh, so cos is analytic in this domain D. That is why we are able to use this result. Now we will do some problems using the first evaluation method. Now the question is integral 0 to 1 plus I z square dz. Okay, so z square is an analytic function, so integral of z square is z cube by 3. You can use the same formulas in the case of real functions. Integral of x square is x cube by 3. So integral of z square is z cube by 3 within the limits 0 to 1 plus I. That is 1 plus I the whole cube by 3. A plus b the whole cube is a cube plus b cube plus 3a square b plus 3ab square. Use that formula and expand it, and the final answer is coming out as minus 2 by 3 plus 2 by 3 times I. Now we'll move on to the second question. Second question is integral minus pi I to pi I cos z dz. Now integral of cos x, you know it is sin x. Similarly, in complex domain, integral of cos z is sin z. So sin z within the limits minus pi I to pi I, that is sin pi I minus sin minus pi I. Okay, now sin minus pi I is minus sin pi I, so the sign in between becomes plus. Now sin pi I is I sin h pi. Okay, sin ix is I sin hx. So sin pi I is I sin h pi. So we are substituting sin pi I as I sin h pi, and then the answer comes out as 2 times I sin h pi. Thank you.